next speaker is Jay McCarthy. He's going to get himself set up. Jay is the is founder and CEO, no, CTO, sorry, Chief Technical Officer at Reach. Reach is an awesome language for building Algorand smart contracts. Actually, he's going to tell you a little bit about the fact that you could actually use the same. Yes, when in doubt. No, it's up. No, it's on. All right. No, there. Something is working. Welcome back, everybody. All right, we are so glad to have you here in the Developer Greenhouse today. Jay McCarthy, founder and Chief Technical Officer at Reach. Welcome to the Greenhouse. Take it away.
Thanks, Ryan. So today I'm going to be talking about how to build decentralized applications safely, or at least that's kind of what I'm going to be talking about. What I'm really going to be talking about is how to build them correctly. And what I mean by correctly is that before you build anything, the most important question that you should ask is whether you know what it is that you want to build. Because unless you know what you want to build, there's no way to know whether you built the correct thing. So the fundamental question that I'm going to be talking about over and over and over again here is, do you know what your dApp is supposed to do? So the way I'm going to approach this is to talk about something called model theory, and then I'll go through some examples of how to apply model theory, and at the end I'll talk about some of the tools that are available for applying these things. And successful. Or maybe you won't be successful, but you won't be not successful. You won't lose your money from your application from doing this. I can't guarantee that you'll actually be profitable. So to start off with, what's model theory? The idea of model theory is there are things called theories, which are mathematical objects that describe the source of truth, the thing that is supposed to happen. And there are models, which are the actual behavior. So, for example, a theory is something like a specification that tells you, here's what I wanted to build, and the model is the actual program that you ended up building. At a very high level, every time you do anything, a model, because you are actually doing something in the real world, but there was some earlier goal that you had. And model theory is about the connection between theories and models. Now, there are lots of examples of ways that we could think about defining the theory. So for example, there are explanations in prose. You can write, English documents that describe what your program is supposed to do. You can combine that with mathematical formulae that try to articulate exactly what the operations that you might do are. And most of the time when people talk about theories, this is kind of where they stop. They say theory is about specification. But I think that actually it's important to realize that a lot of things that normal software engineers do are part of building the theory. So for example, if you're building an auction application and you create spreadsheets that talk about what the correct formulas to use are, then that is really part of your theory, and you should consider it that way. Similarly, if you build like an example testing scenario about how you expect your program to be used, that counts as part of the theory. On the other hand, your model is more than just the actual program, because included in the model are the behaviors that your users ultimately take. Because you imagine when you're in theory world that they're going to do one thing, but in reality that they may do something different, and understanding the connection between those two things is important. So to summarize, there's this question of do you know what you want? Theory is when you talk about what you want. Model is what you actually built. So now, the main question of verification is, what is the connection between the theory and the model? And there's lots of different ways to approach answering this question. The most popular one that people do the most is testing. So the idea of testing is that you have a finite amount of execution of the model to see how it conforms to the theory. There are good things and bad things about this. one of the good things about it is that everyone knows how to do it. It's very fast and it's very easy to do. But a fundamental problem of it is that you can only do a finite amount of testing. And in other words, this means that you can only demonstrate that you did not find problems. You cannot demonstrate that you actually did the right thing. You only know that you did the right thing in the domain that you actually tested. A better way to do it is what I'm calling analysis. So the idea of analysis is that we take one aspect of the model, or maybe another way to think about it is one aspect of the theory, and we do an automatic and infinite analysis over that behavior. This might sound really complicated, but almost all engineers have used an analysis of some kind because they've used a type system. Most programming languages have type systems that make it so that you cannot add a number like 5 in a word like an, because adding 5 and an, although 5 ands would be wonderful, it doesn't actually make sense to add these two different kinds of data. And so a type system is a really simple example of an analysis that looks at one aspect of your program and verifies that it doesn't make any mistakes. Now, the good thing about analysis is that you need basically a PhD, and I'm putting PhD in quotation marks, to design the analysis, but you don't need the PhD there when you're using the analysis because it happens automatically. So it continues to be fast and automatic. Another thing that's a good thing about it is that you're using the actual model. This is something that's shared with the testing environment because you're really testing the actual model, not some abstraction of it. The downside, though, is that you are always going to get false negatives when you use analyses. And this is related to an important proof about the theory of mathematics that's called Gödel's incompleteness proof, which basically says that anytime you have a formal system that proves things, you can either prove things that are false, or there are things that are true which you can't prove. In other words, that means that anytime you do an analysis, there's going to be times when you make conservative approximations that say that there might be a mistake, but I don't really know. And the other thing that's kind of bad about analyses is that they typically can only do one aspect of your work. So to use them well, you have to use lots and lots of different analyses. And you should use more and more of them to handle all the different aspects of the theory that you care about. Now finally, the best approach to know the connection between your theory and your model is to do a proof. To do a proof essentially requires you to always have a PhD present watching you at all times. And in fact, probably the PhD is the one that's doing it. The thing that's really great about it is that this is infinite, and it covers all aspects of the connection between the theory and the model. And that means that it can be more accurate. I'm using accuracy in a non-technical sense because technically the false negative problem shows up here in the proof world as well. But typically the completeness is more thorough in the proof world than it is in the analysis world because it's more manual. And it's extremely slow to do this because it is a manual process. And so you would only do this for models that are very, very important. And in fact, it's not really feasible to do proofs about most models in general. And that's because most real model building tools, and remember, I'm using this kind of coded language. When I say model, like think a program, right? Most programming languages that you actually write programs in are totally infeasible to do any sort of proof about. There's no way that you're going to prove anything about a Python program. It's just not plausible. Even more simple languages like C, well, first of all, C is not a simple language. People think it's simple, but it's extremely not simple, are very difficult to do proofs about. So typically, when you're proving things, you're proving things about models that are further from reality. And so anyways, so it's important to understand that this is possible. I mean, it is totally possible to prove things about real software, and sometimes it's necessary to do so, especially when it's extremely important. This is one of the reasons why Algorand publishes proofs about all of their cryptographic systems, because we want to do the best thing for those high-value pieces of the infrastructure. So let's go through some examples of how you would use each one of those three tools, testing, analysis, and proof, to answer questions about the connection between theory and models. Now, one of the main questions is something that is referred to as soundness. So soundness means, does the model respect its own abstractions? The type system that I mentioned before about not adding numbers and strings is an example of soundness. So a question that you could ask is, are there type errors at runtime? So a type error at runtime is, does my program actually try to add 5 and a string together? So I'm not going to go into as great detail on every single one of these questions, but I'm going to choose this one and talk a lot about how this actually works. So a way to test this is to actually run your program on lots of different inputs and make sure that it never throws an exception actually doing this. If you use a programming language like Python, it does not have a type system built into it, so it's not going to check this property for you automatically. The only way to look at your Python program and answer this question would be to actually run it over and over and over again. People have tried to build versions of Python that do type checking, and these are called gradually typed Python. There's something called reticulated Python, which is a tool for type checking Python programs. Now, in the context of building a smart contract on Algorand, if you're going to use PyTeal, the thing that's nice about that is that you actually run your program, compiling your PyTeal program into a Teal program is running your Python program. So you actually don't care about there being type errors in the Python program, because you would see those automatically because the program. The thing about building something on PyTeal, though, is it produces a Teal program. And that Teal program is yet another program. And so we could ask, like, can there be type errors in Teal programs? And the answer is yes, there can. Because Teal programs could accidentally add numbers and strings together. Now, PyTeal can be implemented to do part of this checking, but also the Teal compiler itself, the Teal assembler, tries to do type checking on Teal programs. I say tries to do type checking because there are many circumstances where it gives up and it says, well, I don't know, I can't analyze this, so I'm not sure. I don't know if it really is type safe, and so it no longer analyzes it. So that means that when you compile a normal Teal program, you actually don't know whether or not there could be type errors at runtime. At runtime here means actually sending transactions to the contract. So this is a viable thing that you should be worried about. Other programming languages that target Teal and the AVM do have type systems. So for example, Reach has a type system, and so you cannot write type incorrect programs. However, we are a compiler, so there's this worry that maybe we produce type incorrect programs, so that we produce a program that would have this error. So because we're nervous about that, we've built an analysis, what we call the Teal analysis framework. And so the Teal analysis framework is a verification engine for Teal programs, and we have a more expensive and more refined type analysis for Teal programs that is sound and complete and guarantees that the Teal programs that we produce never have type errors. So if we just take one example of a kind of question you can ask about soundness, that's a way to think about the testing. You could send it a bunch of transactions, make sure they have no mistakes. You could do analysis, and the analysis that you do, you have two options. You can either make it sound, meaning that we'll never make a mistake, or you can make it incomplete, where sometimes it will give you advice and sometimes it won't. And so the actual Teal assembler is incomplete and unsound. So it will say that it has done the type analysis, but it can give the answer yes, no, and maybe. And when it says maybe, it still lets you run your program. Our analysis framework, when we also say yes, no, and maybe, but when it says maybe, we don't let you run your program. So that's an example of what to do about the false negatives that come out of analysis. Finally, it would be possible to do a proof about this property, to prove that a program really was type sound. In this case, though, it's not useful to think about doing a proof about that because we know that high-quality analyses exist, and proofs are always worse if they're expensive because the best analysis frameworks actually can produce proofs, and so we do that with TAF. Okay, So now we can ask I'm not going to go into as much detail as I said, but we can do the same kind of thinking about things like, are there arithmetic overflows in your program? That's an example of a soundness thing. Does it actually parse the arguments to your program correctly? Will it ever try to produce transactions which we know will be invalid and will be rejected by the network? And does it actually respect the real resource limits of the network? For example, one of the things that we know about boxes that were talked about in the last talk is that you can only use 8 box references per transaction. And so that means that if you looked at a program, a question you should ask is, does this program only use as many boxes as references are available? So TAF does that. So TAF analyzes the VM code that we produce and guarantees that we never exceed the resource bounds. And the normal TLAssembler makes no attempt to do this. All right, so that was soundness. Now let's talk about safety. So safety is the property of, does the theory, i.e. what is supposed to happen, contain the model? So that's a fancy way of using set theory to talk about the idea that, does the model do things that aren't allowed? Because if there's something that's in the model that's not in the theory, then that means that the model does something that's illegal. So an example, people generally explain this as, can bad things happen in the program? So you could ask the question, do we ever write the wrong data to disk or to storage? Do we ever make state transitions that we didn't think should happen? Do we ever lose funds? Because losing funds presumably is not in the theory. Or do we ever pay the person who's the wrong person to pay? These questions you can also think about testing, you can think about analysis, and you can think about proof. Another property, another way to think about the connection between models and theories is something called liveness. So this is, does the model contain the theory? So remember, the theory is what is allowed to happen. The model is what actually happens. So the question is, does what actually happen contain what is allowed to happen? If it didn't, then that would mean that there would be some good behaviors that are in the theory that are not inside of the actual behavior. So people generally refer to liveness as, do good things happen? Are the things that are supposed to happen in your program things that actually happen? So presumably, you want your program, when it runs, for the user to actually get paid. And so you can build a test case that makes sure that, okay, well, in this scenario, when we run the auction, Jay really gets his money. That's an example of a testing approach to this. An analysis approach to this would be to think about all possible state transitions and all possible evolutions of the network and make sure that from where you are now, there's a possible path to the good thing happening, no matter where you go. Because every system is an evolving state machine where, like I'm going to do a little physical acting now. So imagine that I'm the start of the program. And what the user can do is they can choose left or they can choose right. They can do one of those things, and then they can go right again, or left, or maybe over here they can only go forward. So there's this whole state machine of paths that I can get there. You can kind of think of it like a maze. At the start of the program, the user is at the start of the maze, and the question is, no matter what choice they make, will they always eventually get to something that's good? Actually, I guess it's kind of like an anti-maze, right? Because the point about a maze is that there's only one right way, but the goal of your program is to make an anti-maze, where no matter what path they take, they will always get to good behavior. So that is the analysis that you want to do when you're asking the question about whether good things happen. In this infinite behavior is the reason why testing is so difficult to verify liveness. Because all programs have basically infinite mazes, and so the only way to approach answering whether or not they have good behavior is to do analysis or proof. It's not really feasible to do testing. So other properties that you might care about is whether you can actually end your program. That's like a really basic liveness property. Okay. Now, another question that you should ask about your model and your theory is one that says, is your theory valid? And what I mean by here is, how does your theory relate to the actual subject matter? And this is kind of a way of thinking that the subject, the human thing in the real world that you care about, that's sort of like the real theory. And anything that you produced that you're calling the theory, it itself is a model of the real world phenomena. Because remember, when I say the word theory, we're talking about things like specifications, and formal methods that describe what you want to happen. But programmer to do anything, one of the things that you'll find is that no matter what specification you wrote, they will make something that follows that specification, but does not solve what you care about. That is an example of an invalid theory, one that does not reflect the real world. And so mathematicians, part of our axioms of faith is something called the Church-Turing thesis. And the Church-Turing thesis essentially says, we declare that all our theories are valid. When you say the word computation, you're talking about a Turing machine. So therefore, anytime people think about computations, they must be thinking about our theory. And so people think that the Church-Turing thesis means something different, but that's what it means. It's a statement of faith that we are always right when we do analysis. And so, but this is something you should be very stressed out about, the validity of your specification. All right, let's apply these 4 different ways of thinking about what is worth checking between models and theories to the auction application that the workshops for the rest of the day will be going through. So let's start off by asking a really basic question about validity, about do you even want a dApp? So what we might want, so the premise of an auction application is that think eBay, but related to blockchain. So we have something that we care about buying. Everyone, I'm doing a performance right now. The clothes that people wore on famous performances are, hot topic items. So I will be auctioning off this shirt later today. Okay? So you too can have the opportunity of being part of Jay's talk at Decipher. So one way that we could do this is building a centralized application, or a CRAP. So a centralized application is a traditional one where all of the data is stored in a centralized place, and there's all sorts of advantages to centralized applications. They're extremely fast. They're very easy to build. It's easy to query them, easy to build servers, easy to build clients. They're very flexible because you can change them whenever you want. There's a reason why people love CRAP. Now, the thing is that there are 2 disadvantages to CRAP. They only trust it because of their being embedded in a legal system. Because if you dispute something that eBay does, the only recourse that you have is essentially to sue them or to hope that society will help you and shame eBay into doing what you want. The other problem with them is that they're closed, so we don't know whether or not they're really doing the things that we want. In other words, it's very difficult to trust the model of a CRAP because you can't see what it actually is. Now, the reason we're here, of course, because we love dApps, but it's worthwhile to point out that there is a point of using CRAPs in the blockchain world, because eBay would be better if you could buy things with algos, because then the payment mechanism would have all the advantages of using Algorand relative to using PayPal, which is the most common thing that people use on eBay right now. So I am, of course, a little bit of making fun of centralized applications, but it is worthwhile to build centralized applications that have a connection to blockchain. And it may be for your domain, it is worthwhile to auction off my t-shirt using an eBay, but where you pay with algos. It's feasible that this would be a good thing. Now, a dApp, of course, has advantages, but there are 2 kinds of dApps. There are what are traditionally called dApps, and a subset that I'm going to distinguish as DDApps, or protocols. The essential difference between these is that a dApp is one contract that has the behavior that you want, and the other one is a network of contracts that all speak a common language, doing the same common thing. So in the context of an auction, a dApp would be one contract that manages all auctions. And a protocol would be every auction is a different contract, and they all speak the same language. Right now, when you use a website like eBay, you're speaking to a dApp-style thing. You're speaking to one website. But when you use email, you're using a protocol because everybody has their own email server they all speak the same language, but it makes it so that people can run their own. Now, there are pros and cons to these 2 things. They're both trusted by code rather than by law, which is an advantage. But in some ways, the dApp has disadvantages because The main things that are disadvantages about it are that, like all blockchain programs, they're slow. No matter how fast Algorand is, it's not as fast as AWS. When I say slow here, I'm comparing the Algorand world to AWS, not to Ethereum, where of course they're snails, and where we're not. AWS is a Ferrari, Algorand is a cheetah, and Ethereum is a snail. Okay, so in the world of animals, it's great to be the cheetah, but I want to drive a Ferrari. Okay. Now the thing though is that the dApp, in some ways, is more flexible because is less flexible because you can never change the contract once you launch it. You're stuck with that particular program. In the protocol, all you have to do is maintain the same interface. So every single auction can be a different program over time. So it means that ultimately it becomes more flexible. It's more open as well because you're going to have to build clients that work with any given instance of the protocol. But people can then make their own versions of it. So in the decentralized world, there's a strong predisposition to prefer protocols, but from an engineering perspective, people tend to build and want to build dApps. So when we're building our auction, we should think about this. I believe that all the auctions that you'll see later today are in that middle category, not the protocol. So let's think about how we would think about the theory and model for our auction. There's lots of things that go into the theory. There's things like, there's a Wikipedia article that explains English auctions versus non-English auctions versus this kind of auction versus that. Like, that is part of your theory. What is the auction mechanism that you're going to choose? You're going to write a PDF in English that's going to explain what the auction is supposed to do. You're going to have some formulas for figuring out the prices. You're going to have like a manual for testing your program. You're going to have a suite of tests for the contract. You're going to have tests for the client. You're going to have tests for the UI. All of these things are part of your theory, and you should build them all. Over on the model side, you're going to have your actual program, your Reach program, your PyTeal program, but then you're also going to have the bytecode blob that gets produced by the assembler. That's the real thing that runs, not the Reach or PyTeal program, and that is part of the model. Those are some of the artifacts that matter. You're going to write a client library, presumably in JavaScript, and that becomes part of the attack surface of your program. Because if there's an error in the client library, the auction is still compromised. You're going to build a UI. You're going to use the Algorand SDK. You even have to think about whether or not the Algorand Go node implementation is correct. You're going to have to worry about whether the hardware that mainnet nodes are running on is compromised. It was mentioned in a panel that cryptographers don't sleep well at night. That's because when you really start thinking about all of the potential attack vectors for your program, it includes pretty much everything. And there's all sorts of mechanisms that are built into the design of decentralized networks to protect against a lot of these things on the bottom. So it's not worthwhile for you to think about these when you're thinking about your auction application, but that is kind of the point of blockchain, that all of those problems have already been solved, and you get to focus on only yours. But if you were designing an auction application that was decentralized from the start, and you had to do everything that blockchain provides for you automatically, you would never get off the ground. So let's think about soundness. So we want to ask the question like, do we really obey the ABI types? Do we have any type errors? These are the things that we talked about before. So I spent the most time before about this, but I want to highlight one, which is that does your client verify that the contract that it's talking to is actually the right bytecode? Because you could have a user interface that is talking to an application on mainnet that you don't check that it's actually the right one. It has the same interface, but it's not using the right bytecode. There have been real attacks of real actual blockchain programs where the AWS site serving the client was compromised, and it just redirected people to a different contract, and they lost all their money because they used it. For safety, we want to ask questions like, does the contract end with an empty balance? Because we're going to have an auction, and we presumably want the funds to be given back to everybody. And if you end the program, then all the funds are stuck there forever, so that's a very important property to ask. When we think about liveness, questions are things like, do losers of the auction get their money back? That would be an example of something that we really want to make sure is in the program. We want to make sure that the winner really does get the asset. We want to make sure that the prices can be arbitrarily large, because we want to have the problem of people, risking billions to buy my shirt. Another example is, can the application index be this number? So the application index is a 64-bit number on the actual Algorand network, but the current SDKs in JavaScript do not accept this number. So right now there's a latent error in the Algorand SDK that if this number ever gets returned by the network, which it is possible to do, then all the SDKs will fail to actually run and deal with the program. The explanation for why we're okay with this error is that we know that the application ID is actually generated by the block number, and this block number will only occur in 2,000 years or something like that. So it's somebody else's problem. So we have, from now until then, unless we change the application ID generation rules to deal with this problem. So the other question about validity is, did we even want to use auctions, and did we choose the right auction mechanism? In particular, is it good to use an auction mechanism that is attached to the blockchain? Because we know that all blockchain things are intrinsically public. And so do we want to know that, like Ryan, he's waiting to bid $100 on my shirt because he's just dying to get my shirt? And does he want his wife to know that? You know what I mean? These are the kinds of questions that you need to ask when you're thinking about actually building a real blockchain application. And this is one of the reasons why there's so much interest in things like snarks and homomorphic encryption and ways of having privacy-preserving applications on blockchain. Those are not questions about soundness, liveness, etc. Those are questions about validity. Can we build the things that we really want to build, that our users really need? We shouldn't just accept that it's always going to be right. So some of the available tools for doing this, I'm going to just point out 3 of them. So the first one is the Teal analysis framework. That's the thing that's built into Reach that does all sorts of soundness and safety analysis for your program every time it compiles. This really has nothing to do with Reach itself. It's just analyses on Teal programs. With Reach, all of these things are being checked. There's also SMT solvers, which is a really good tool for doing safety analysis. Essentially what SMT solvers do is they take a model of your program, which is a set of equations derived from the source code, in particular the Teal source code, and they check to make sure that the actual behavior is contained inside of the theory, and they can do it automatically. Another tool that's very valuable is something called Alloy. So Alloy is a model checker. What it does is it's really optimized for doing the other thing, the liveness property checking. Because what it can do is you can describe the state transitions of your program, and it performs that creates an infinite state space, and you can ask questions about where it goes along there. Another tool that's popular in this world is not Alloy, but the K framework. So you've ever heard of the K framework, which is one of the tools that runtime verification uses? This is what it does. So this is what I wanted to talk about today. Do you know what you actually want, and how can you check to make sure that what you built actually is what you want? This is the fundamental question you should be asking when you're worried about building a program correctly. And once you start teasing apart what it really is that you want, and saying, I want this, did I really do that? I want this, did I really do that? That is what it means to build something correctly. And there are all sorts of mathematical and software tools that can help you answer that question. And there are all sorts of people in the Algorand community that would love to help you answer this question for you. Thank you so much for your time.
Jay McCarthy, everyone. Thank you so much, Jay. I always enjoy listening to your talks because you break down complex things in a simple way. And I think what not to discount what you said because it was all fantastic, but clearly I broke it down as ands are great and Fox doesn't fit in your shirt. No. Everybody, give it up one more time for Jay McCarthy.